Okay, first things first, even though it kind of messes with your brain, the first thing would be to make this the positive direction and call that forward. Since friction, the coefficient there is always between 1 and 0 in a realistic physics problem, um, we can assume that, so it can only pull with up to its weight. Like this one could resist with up to 10 newtons, 10 times 1 kilo of friction, but not more, okay, unless it's really sticky engineered material. Okay, so 20 newtons pulling over the tabletop edge is going to overpower 10. So we're going to go that way. So let's call that way forward. And so this way forward is up here. This is also to the right is forward there, and down is forward once we're off the table edge. Okay, so separate force diagrams. We might need that for the tension. Okay, we'll do M1 first. It's going to have a force of tension. You could use capital T if you like one symbol. It's going to have its normal force. Of course it has M1G. And it's got a friction force. Let's do the curvy F, force of friction. Okay. Is our normal force equal to M1G in magnitude this time? Yeah, it will be, because no angles, right? There's nothing else pulling on it. Okay? And we only introduce friction. Friction is the force parallel to the surface. Okay, just dragging along, resisting the motion. And there's nothing pulling at an angle. There's nothing else affecting it. Okay? So we probably finally get the sense that we actually know everything in these physics problems. Or you can assume there's nothing else to it. Okay? All right. So those two completely cancel. The force of friction, yeah, I think it says cursive F or something, is just that mu coefficient times your normal force. Okay. So that's 0.75 times 10 newtons, so 7.5 newtons. Okay. So then we free body diagram each one. Here's M2. It has M2G, or 20 newtons, going down, and it has less force of tension going up. Okay. Any questions? Sure. For M1, I don't know. It has to be the same because they're connected by the same rope, so everywhere in the rope has to have the same tension. I don't know what it is. We're going to get it along the way. Okay. Good question. Okay. So on the test, it'll be like a third, depending how many points, how many answers the question has and how many points. So this one, it would be maybe fourth. But it'll be 1 point for the question to have the appropriate free body diagrams. Okay, and they don't have to be perfect. The arrows don't have to be appropriate size. I think it helps you understand if they are. But they need to you need to have all the relevant arrows included and labeled. Okay. I want to do kind of a zoomed in one, because this is really one system, right? We have our pulley there, and we have our system of M1 and M2. Right? We could have, and actually that's a silly diagram. We can, since we're measuring along this one forward x-axis, we can really just imagine that here's a system of M1 and M2, and it's got 20 newtons for M2G pulling to the right, forward, in the plus direction, and it's got 7.5 pulling back. And there's a total of 3 kilograms in the middle. Okay. And so actually, if it wasn't Friday, if we weren't asleep and relaxing, mad at that video because it was too long and had silly stuff, if we were thinking clearly, that actually solves the problem. Can I just take 20 minus 7.5 and divide by 3 and that's acceleration? Yep. Yeah, you can. Okay. But here's the proof I'm going to need on the test to show me that you understand. Okay. I need you to actually write the acceleration equals, if you hate that sigma letter, you can write F net over m, and maybe even m total if you have two masses. Okay? Newton's second law. Write the equation, and then you can plug in your forces, whether you want to say m2g or 20 newtons. Okay, I've got plus 20 newtons minus 7.5 over, I actually want to write 2 kilograms plus 1 kilograms. So I have the given information, I have plugged in. Okay, the tension is an internal force, action-reaction. Look, if I put one tension arrow pointing forward, yeah it does, the other one points back. So if I actually put the tension in the equation, there would be plus Ft and minus Ft. It would automatically cancel out. Okay, if I added up all the forces on these objects. Okay, can I do that in my head? I think so. It's like 4.16 repeating. We'll just say 4.17 meters per second squared. Okay, it's not the 6.6 repeating that you would get up there. Now, how do I solve for the tension itself? Did you catch me? So there's your acceleration. Did you catch me messing with you the other day? I made every single class start with the big mass. When really that was kind of silly. To find, now that I know the acceleration, to find the force of tension in m2g, I just free body diagram this one alone. Leave off the pulley, leave off everything. Okay? And then so the acceleration of m2 has to be plus m2g, which is 20, because that's my, remember that's forward. Can't change my axis in the middle of the problem. Minus f of t divided by m2, which is 2. And that has to equal 4.17 because they're hooked together and they accelerate the same. So in a problem like this, or the Atwood's machine, you definitely need the acceleration first. You can't solve the tension until you know the acceleration. Okay, the same with the penguin. Like I could give you everything but the force of tension, and you'd have to plug it in backwards. Okay, the penguin really is attached to something else that's pulling him in the previous example. Okay. Oh, there it was. Okay. It's got 4.16 repeating times 2 for the M2. What's that? Minus 20. And then times negative 1. Okay. So my force of tension should be 11.7 newtons. Just solve for that. This is positive. This is positive. Negative sign makes it work. If you tried the horizontal block and you had its force of friction, 7.5 pointing back and the mass of 1, oh, that might have been easier again. Oh well. But if you try that, if you free body diagram the horizontal block, the M1 that's sitting on the table, you should still get 11.7 or 11.6 repeating. Okay. Any questions? Got one more, and it's super easy. And then we can look at reports or answer homework questions. Anybody still need that? Well, we got lots of time. We'll put them together. Okay. If you have a falling object and I give its mass and acceleration, you can calculate the force of air resistance. If I say a person is in an elevator accelerating down, or a gymnast in the homework is on a rope climbing up, that's all you have to do. Okay, your acceleration is the net force over the mass. Okay, so that says -2 acceleration units. The net force is always mg. Watch out, I said grams, I was mean here in this example. So that's 0.05 Newton, 0.05 kilograms, so that's 0.50 newtons, okay, plus the air resistance that points up, divided by the mass, 0.050 kilograms. Okay, if you like MA, you could also do mass times acceleration equals force of gravity, or mg. Let's do mg. mg plus f. And make sure those are vectors, right? So with the gymnast accelerates up, gravity points down. There must be a force. Mass times acceleration, mass times 10, pointed down, and then plus f. That's the force on him. Okay, and that's the tension. So he pulls down on the rope in the homework, and the rope pulls him up, action, reaction. Let's use the calculator. 2 times 0.05 plus 0.5 is 0.4. So if I have a balloon that weighs 0.5 newtons, because it's 0.05 kilos, and it's accelerating down, oh look, at 1/5 of gravity, well then 4/5 of gravity must be canceled out. Okay. It just takes time to get used to these problems. Maybe it's me, how I make everything so complicated. Sorry, I couldn't hear you. Why is the 0.50 negative? Because gravity is going to point down. Oh no! Oh, I didn't see my own notes. I don't like that at all. Things are falling down. I want y to be positive, up. I disagree with old Mr. Watson's notes. Okay, it works the same either way. But if you like this acceleration down, like I made it negative. Oh, and you wouldn't accelerate up because of air resistance. You need some sort of motor or lift. Okay. I'm sorry I left that plus y down arrow on there. Okay, so that's why. It's Friday for me too. Yeah. No, I like down as negative whenever I can get it. Sometimes though, like if we have a pulley, there's a pulley involved, you got to make forward positive. Or if you're sliding down the ramp, that should be positive, just to save yourself the opportunity to forget negative signs. Okay. Good. That's a great question. Any other questions? Sure.
How much off is it going to be if we like mess up the negative sign on the test?
Oh, if I can see, so a problem like this one would only be worth 3 points to set up the body diagram for formulas and calculations. That's 1 point each. If I can see exactly the mistake you made, that's half a point off. If I can see the one thing that went through the rest of your answers, yeah.
On problem 16 on homework,
Yeah.
we set the force in the acceleration as positive or negative.
Okay. I'll answer your question, and then I should just go ahead and do the example for them online.